When thousands of automated tests are running, continuous integration flows like electricity. But the moment a critical test halts, the entire pipeline stops. Writing automated tests has become efficient, but finding the root cause of an unexpected failure remains a significant resource drain. Standard diagnostic evidence is often limited to a block of raw text. A cryptic stack trace spit out into a terminal identifies where the code stopped, but it provides little context regarding how the application actually behaved. Relying on error screenshots adds further complications. Modern web applications are dynamic ecosystems of changing states and hidden elements, and a flat image of a frozen browser window cannot explain the underlying logic. Recording every execution as a video file introduces its own penalties. It increases storage requirements and slows down the pipeline, yet engineers are still left observing surface-level pixels instead of the actual code state. Diagnosing a failure requires manual cross-referencing. Engineers compare timestamps from text logs against frames in video files, attempting to map visual pixels back to the specific logic that failed in the stack trace. Playwright addresses this information gap with the trace viewer. Instead of a static capture, it preserves a highly compressed, interactive microenvironment of the exact millisecond the failure occurred. This changes the engineering workflow. Rather than observing a representation of a failure from the outside, you step directly into the live application state at the moment of the crash. You stop relying on theories about what happened and look directly at the technical evidence. This timeline maps test actions sequentially. An engineer scrubs through granular milliseconds to target specific interactions. Selecting an action node reveals 3 distinct states. You see the application precisely before the event, the exact millisecond of the input, and the immediate aftermath. Playwright captures the document object model itself. Every state is a fully interactive snapshot of the underlying code. Because the actual DOM is preserved, you can open standard developer tools inside this recording to inspect the HTML structure, CSS classes, and element properties. A flat screenshot limits you to visual observations. A DOM snapshot allows you to click into the page, inspect the shadow DOM, and verify element attributes that aren't visible on the surface. Diagnostic visibility requires interacting with the code exactly as it existed in the past, rather than settling for a static image. Often, an unresponsive element on the screen is merely a symptom. A missing data table or a broken button usually points to a back-end failure, requiring telemetry that goes deeper than the UI layer. The trace viewer provides a synchronized network tab. Clicking an action filters network requests to that exact millisecond. If a request returns a 500 error, you expand it to read response headers and the failed payload, eliminating the need to hunt through separate server logs. Simultaneously, the source mapping feature highlights the specific line of TypeScript code that was executing at that moment. The DOM state, the network traffic, and the source code function as a single synchronized record. By aligning the UI result with the backend response and the specific code line, the infrastructure provides a complete technical account of the execution. Capturing this level of granular data for every action could potentially slow a CI/CD pipeline. Processing DOM snapshots and network payloads for thousands of tests creates a significant computational load. Playwright manages this through a configuration parameter known as trace on first retry. Under this configuration, automated tests execute at their native speed. During a normal passing run, 0 telemetry data is captured, which minimizes the load on both computation and storage. Forensic data capture is triggered conditionally. It activates only if a test fails and the system initiates a retry, ensuring that traces are recorded only when they are needed for debugging. This architecture allows engineering teams to maintain fast deployment speeds without sacrificing diagnostic depth when errors occur. All of this evidence is compiled into a standalone, compressed file, the trace zip. This file functions as a progressive web app, meaning it can be analyzed in any browser. It does not require proprietary software or a connection to a backend server to function. This structure simplifies collaboration. Developers can share the trace file across global teams, providing a consistent record of the failure without exposing secure company data to external platforms. The trace viewer shifts QA culture, replacing debates over why a test failed with a technical record of exactly what occurred.